lecture 39. We've moved into the last week where we're gonna utilize some of the tools and learn new tools in order to analyze some experimental data. Many of you, I'm sure, take interest in experiments, and during experiments you obviously collect a lot of data. Data collection is not what it used to be, what it was in your school days or something. It's now more electronic. There's data loggers, all sorts of sensors, temperature sensors, pressure sensors, things like that. And so in this electronic age, it is expected that once you have data, you're going to analyze the data and get something useful out of it. Right? So in this particular lecture, we're going to touch upon a bit of audio processing. Well, I call it audio processing, but more generally, it is signal processing. So a few days back, I was tuning the carburetor of my bike, and once I switch it on, I can see the meter on the bike. It says something close to 1500 rpm, and it's something which you can make out clearly. It's a sort of noise. It's not too fast, it's not too slow. Okay, so then that gave me an idea whether you can predict or tell what the rpm of a certain device is with some audio clues. And what is audio? I mean, whatever you perceive as sound is really how a pressure fluctuation is reaching your microphone or your ear, right? And whenever you have various machines that whiz or whir that go around you, for example, the fridge compressor or your fan or some high frequency sound of an insect, sort of associated with some kind of periodic motion that that particular device or insect is making, right? So in this lecture, we're gonna see how we can predict the RPM of two machines that I had. I mean, in the workshop. So the first machine is the bench grinder, and the other machine is a simple pedestal fan. And well, everyone knows what a pedestal fan is. It's one of those fans which has a base. It has a long stem. Then from the side it looks something like this. There's a shroud, and there's three blades like this, and this goes to mains. So it's a device which runs off mains, and it does have an AC induction motor. Okay, a bench grinder is also something similar. How it looks like is there's a central bearing holder, and then there's two shafts, and there's two wheels connected. So these are sintered grits of aluminum oxide, carborundum, whatever it is. It's a device where these two discs rotate, and you can sharpen various things. So it's called as a bench grinder. It's also AC induction motor, but whether or not they have the same frequency, well, AC machines they run at synchronous speeds. this is quite different from how other kinds of motors, for example, DC motors or universal motors run. Okay, so induction motors have a synchronous speed. Well, not all kinds of induction motors. There's different kinds like shaded pole motors which don't run at in synchronous speeds. Um, DC motors have a large speed regulation depending on the load. Universal motors tend to run at significantly higher RPMs, and that also depends on the load. But AC induction motors, the one you find in your ceiling fan and all these kinds of appliances, they run at synchronous speeds. The synchronous speed is dependent on the number of poles, the frequency. Okay, so if you have 50 hertz as the AC mains frequency, so the synchronous speed will be something like 1500 RPM, and the formula is quite so let me just show that formula. Hmm, so it's simply equal to 120 times F by P. Okay, so for a single phase 4 pole, so this is for a 4 pole motor, and the formula is 60 F, rather 120 F by P. Right, so these are the number of pairs. Okay, so 120 times 50 by 4, total number of poles. So there's 2 pairs, but there's 4 poles. So 30, and this gives you something like 1500. Right, so that's the RPM that we have of the motor, and that RPM of the motor when converted to hertz. So you cannot just say that this is the hertz at which the motor is running at, because the number of poles are different, and so the corresponding hertz or per second calculation, cycles per second, is 1500 by 60. Right, so that's the hertz of the device. So what do we get? 75 by 3, 25. So we have 25 hertz as the frequency of a 4 pole induction motor. And let us see whether we can predict that the RPM of this induction motor is something which we can get from an audio source. And how do you actually find the frequency? So how do you actually do it? Well, you use a tachometer. There's various kinds of meters. You can attach it to the spindle, it rotates, or you can use a strobe. Okay, so in your basic electrical machines lab, you might have done something like this, but we don't bother with all this. These are sort of, well, this is a non-contact method. Yeah, it requires you to have a stroboscope. This requires you to have a tachometer. There's laser tachometers as well. The old kind, it involves you mating the spindle of the tachometer with the rotating shaft. But let's see whether we can do something even simpler. So what I did is I took my mobile phone, I kept it over here, and I turned on sound recording when the fan was on, and I took my mobile phone and I kept it on the casing of this bench grinder, and I recorded a bit of audio. How that audio can give me insight into the frequency of rotation of the motor is what we're gonna study. Okay, so we are going away from the traditional techniques, something which is quite cheap. You can do it at your home as well. And at the end of the lecture, I do hope that you will take this technique and try to figure out various the running frequencies of various motors or things around your house. Okay, so let me go to Jupyter Lab. So what? So these are the old files. So let me create a new file. It's Python 3. I don't know why there's a bug, but I need to select it again from here. So I've created a new file. Let me rename it as like 39. Alright. So first things first, let us declare what this program is going to be about. It's going to be about audio. Alright. So let us import the usual things. We will require numpy and all this. So let me run this. And what I did was I recorded this mp3 because my audio recorder, the audio recorder I have in my mobile phone, it gives me an output in mp3. In order to process the audio files, I need to have it in .wav format. And how I did it was I went to the command prompt, I navigated to the folder, and I executed a command in ffmpeg. So ffmpeg is a set of encoders and decoders, very efficient, and I gave an input file as tablefan.mp3 and the output file as tablefan.wav. So .wav file, let me go over here and get the media info. Maybe it's a bit too small to read, but yeah, this gives you all the information. But we can fetch all this information from Python as well. So before going to that, we need to import the module which is going to help us to import a .wav file. Okay, so import scipy.io.wav file as sw, and let me run this cell. So let's do it. So samples comma data sam comma d is sw.read. We're gonna give the name of the file. So the first file we're gonna analyze is the table fan. So table fan dot wave. Alright, so let me run this. So we've loaded the wave file, and what do the sam and d contain? So let me print out what sam is. It's 1600, and let me print out what d is. But it's a big array, but we can query the size. So it's an array of size 32,000. No, it's 3,22,560. So it's 322,560. All right. So what is this 1600? It's the sampling rate of the file, meaning that audio file has, in one cycle, it has 16,000 samples. Okay, so it's samples per second. So it's 16 kilohertz basically. And so the number of the size of d, that is, so d contains the data. So d is, it looks roughly 20 times what this number is, meaning that the file we expect to be of 20 seconds duration. So let us see whether it is really 20 seconds. So let's go over here. Let me query the media info, and it is 20 seconds. Great. So what it is table fan So table fan dot wave is a file of 20 seconds. 1 second contains 16,000 samples, and that is what the information we have. And D is obviously the data. So what we can do is we can plot the data. So plt dot plot, and we can simply plot D. This is the data, right? And it's just a bunch of waveforms. So let me pick out a small waveform, so that let me pick out something between a million or this to something like this. It's just a waveform. Can't really understand anything from a waveform, can you? That's where Fourier transforms come into the picture. So well, let me declare n as np dot size of d. That's the total number of samples, right? So on the one hand we have d, on the other hand we have the sample rate, and n. So we can actually create an array. So we can create t equal to np dot arrange n times 1 over sample. Just to make the time axis, we can plot t comma d. So that gives us 20 seconds. So basically what we have over here is it's the audio signal near a fan. Let me suppress this. Right, so far so good. But how do I make sense of this data? I mean, there's too much data in this. I don't know what frequencies it contains. And by now you might have guessed that, okay, he's gonna take a Fourier transform of it and find out the frequencies. And if you've thought this, you're absolutely correct. That is exactly what we're gonna do. Just to give you a small background, so we're gonna do a discrete Fourier transform, and it's called as a fast Fourier transform. And what this is going to contain do is do the following. So it's gonna take a signal x n, where n goes from 0 to n minus 1. It's gonna transform it to the from time domain to frequency domain. So we have y of k as sum of n equal to 0 to n minus 1 e to the power minus 2 pi I times kn by capital N times xn. And you may recognize this as being the discrete form of the continuous Fourier transform. And similarly, the inverse transform is nothing but 1 over n summation k equal to 0 to n minus 1 e to the power 2 pi I kn by n y of k, where I is imaginary number, I is square root of minus 1. So what this does, it's gonna pick out the amplitude of that particular frequency. So this is an indicator that given a certain frequency n, what is the amplitude of that particular wave. Imagine you have x equal to sine of 5 times 2 pi t, right? So when n equal to 5, it's going to be 1. For all the other n's, it's going to be 0, right? So this is what the interpretation is going to be. It's going to isolate each wave component, but it's not going to go over all the frequencies. It's going to go from 2 pi times 0 by n to 2 pi n minus 1 by n. So it's going to go over the discrete frequencies. Alright, so we're going to take a Fourier transform of all this. So for that we have to import the Fourier. So let us import all those. So we have to import FFT. So from scipy dot transform, oh sorry, import FFT comma FFT fric, and I'll tell you what these two functions are. So after importing this, we're gonna take a Fourier transform of the data. So the data is D, so let me call dk as the transform data. So dk will be FFT of D. Alright, let us see what how dk looks like. So plt dot plot dk, and it looks very weird, okay, but there is a certain way in which we must plot this. But before even plotting, let me show you what dk has. So let me first of all print dk. Well, let me tell you the ordering of what dk is. So once you take a Fourier transform, it arranges the terms in a very peculiar fashion. It goes from the following sequence of k. It goes from 0, 1, 2, all the way to n by 2 minus 1 for the positive frequencies. For the negative frequencies, it goes in the reverse order. Okay, it goes in the reverse order. And this particular sequence you can get using the FFT fric function as well. So once you have dk, it is customary to also get the frequency points. So let me call them as xk as FFT fric, and this has the total number of sample points and an additional input, which is 1 over the sampling, uh, 1 over the sampling frequency. So it's going to be 1.0 divided by sam. Alright, so why that 1 over sam? Because once you have this ordering, you must realize that you're not sampling over all the frequencies. The maximum frequency you're going to sample, or rather the smallest time interval, that is going to be 1 over 16,000. Not yeah, 16,000. That's this per cycle, that's the smallest delta t that exists. All right, so that is the inverse of that is going to be the frequency. Actually, let me put it this way. So you have 16,000 samples per second, so per cycle. So one cycle consists of 1 over 16,000 cycles per sample. Okay, so that is the smallest unit you have, and that is what you need to give to the FFT frequency to tell that this is the step unit of the frequency. Okay, so this will give you xk. So far so good. Apart from this, if you look at the formula over here, if you set if you set k equal to 0, then it is simply the following sum. If you set k equal to 0 and you have y 0, as summation of n equal to 0 to n minus 1 e to the power 0 times xn, and it is simply the sum of all the peaks. Okay, so let us see whether that is true. So we're gonna plot the two quantities. So q1 is sum, or np dot sum of all decays, and q2 is gonna be the Fourier transform but the zeroth mode. So let us now print q1 and print q2. Ah, this is not going to be sum of decay, it's going to be sum of d. Alright, so look, it does check out. The sum of all the data points is equal to the zeroth, or the, once you set the k equal to 0, the Fourier transform at the zeroth frequency, if you will. Okay, that gives you the sum. So that's true. So we verified this. Now we can proceed to show another thing, that it's symmetric. The distribution is symmetric, meaning the first term and the n minus 1th term will simply be complex conjugates, because these are all the positive frequencies. Sorry, these are all the positive frequencies, these are all the negative frequencies. So let me show that as well. In order to show that, I'm gonna assign q1 to dk1 and this as n minus 1. So as you can see, they are simply complex conjugates. So it is good enough if we can simply plot half the values. We don't need to take all the values into consideration. Okay, so in order to take half the values, we can simply take n ceiling 2. Right, sorry. So in case you're wondering what that operator means, let me show you. Okay, it's the lowest, is the floor function. Okay, it is the floor function. So essentially we are picking out only half the range. So once we've picked out half the range, what do? We can now make a plot of it. So let me do that. So we're gonna plot xk and the magnitude of dk. So np dot abs of dk. So let's see. Okay, we have something. Things are very crowded, but we do expect things to be crowded near the small numbers. So that's why we make a log of it. So instead of plot, we do a log. Alright, so this is the log plot for the fan problem. Alright, so now from this plot, you see that at a certain frequency, there's a peak in the amplitude, and this frequency is something near, well, it has different modes. This. So we'd like to isolate those modes. Alright, so let us try to isolate those modes. We have done this before as well. In order to isolate the modes, we're going to use the scipy function peaks, find peaks. So let us import that as well. So from scipy.signal. Import find peaks. Alright, let me run that. Now we're gonna say peaks comma nothing is equal to find peaks of decay. Height of the peak should be above 10 to the power 7, and the distance between the peaks has to be maybe 200 array points. Right, so once we've done this, so let's do plt.log xk of peaks comma np.abs of dk peaks. Let us mark them as x red. So let's see what we have. Alright, so we do have the peaks, but okay, I think, yeah, because find peaks we need to give it np.abs. Alright, great. So now we do have the peaks. Let us see what the values of the peaks are. Okay, so let me simply plot the frequencies at which the peaks occur. So xk peaks, print xk peaks. Alright, so it's 25, 51, 77, 103, and so on. What is the frequency that we had found out? And yeah, for a synchronous motor it does come out to be 25 hertz, and that's great. I mean you could figure that out using a very simple program. I mean it literally is a few lines of code and audio signal with which you could figure out what that frequency of operation is, and you do see that you get multiples of those frequency like 25, 51, 77, 100. So it's like 25, 50, 75, 100, 125, and so on. And I'm going to bet that this is something like 12.5. So let me just reduce the threshold of the peak finding function. Let me make it 1.6. Let me run it, and let me see what this contains. Okay, it contains a bunch of values because it's grabbing this as well. I don't want to grab this. Well, it should be the second peak, and it is actually 12.89. Good enough. So we are getting all those harmonics. It's, let me revert back to 1.7. So the real peak occurs at something like 77. Now, okay, we're gonna go with the primary peak, which is 77. Alright, so what do we have from the audio signal? So from the audio signal, for a pedestal fan, we have a peak at 77 hertz. Right, that is the peak signal. All the other signals are sort of at least a decade smaller in magnitude than that peak signal. But why 77? I thought it was supposed to be 25, no? And the reason is clear. There's three fans, there's three blades in the fan. The three blades are cutting air thrice in one cycle. So we must divide this by 3 to get the true frequency of the fan. Okay, so in a cycle you're getting 3 pressure fluctuations because of the presence of 3 blades, and hence it comes out something close to 25 hertz, which corresponds to the synchronous speed of the AC motor. And that's quite fantastic. I mean, think about it. You were able to get a very good estimate of the synchronous speed just by the audio signal. No fancy electronics, nothing, just an audio recorder. Well, not so fast. Let us change the input file to the bench grinder, and let us run the entire thing again for a bench grinder. In fact, let me make a new set of cells. So we imported all this. I'm just gonna change this to bench grinder, and I'm gonna write this as audio signal near bench grinder. Let me run this cell. Let me see whether it gives me the same synchronous speed, and the answer is no. Well, what is this blue plot? Let us see. We are plotting everything in, so let us suppress this particular plot. Alright, so for a bench grinder, the peak frequency appears to be around this, which is 50 hertz. Well, that changes everything. So for the bench grinder, it is around 50 hertz, and you have multiples of 50 hertz. Those are the overtones, so to say, 50, 100, 150, 200, and so on. And that's fine, but 50 hertz. And the fact of the matter is, I checked the label of the bench grinder, and it did say that the bench grinder runs at 3000 rpm and not 15,000 rpm. What could be the reason it runs at 3000 rpm? The reason is over here, instead of having 4 poles, it has 2 poles. So the AC motor of a bench grinder, it has 2 poles, so it's 120 times 50 by 2, and it does give you 3000 rpm. Alright, so 3000 rpm corresponds to 50 hertz, and voila, you do have a good estimate of what the synchronous speed of the bench grinder is. Typically, bench grinders have a higher speed because you're doing a lot of grinding. In order to have good material removal rate, you need to have a high RPM in the grinder. So with the help of this simple experiment, you are able to figure out all the different frequencies that are at play. So with this, I'm gonna conclude this experiment. All the sound files will be up for upload, and you can try this piece of sample code for many rotodynamic machines in and around your place. So with this, I say goodbye. I'll see you again next time.